Today, we're tackling one of the absolute most asked coding interview questions in the entire world, the two-sum problem. Let's jump right into this explainer and see exactly how to master it.
We're going to treat this just like a real interview session. So we'll start with that naive first instinct you might have, and then we'll move straight through to a totally elegant, highly optimized solution.
All right, so here is Leetcode problem number 1. You're given an array of integers called nums and an integer target. Your job? Just return the indices of the two numbers that add up to that target. Now, crucially, you can assume exactly one solution exists, and no, you cannot use the exact same element twice.
Let's look at an example. If our array is 2, 7, 11, and 15, and our target is 9, our output is going to be 0 and 1. Why? Well, because the number at index 0, which is 2, plus the number at index 1, which is 7, equals 9. It's that simple. But with arrays sometimes having up to 10,000 elements in real interviews, optimization really matters. So let's first look at the obvious way.
Section 1. The brute force approach, the obvious way. The logic here is essentially just a double-nested loop. First, you fix an element using an outer loop, I. Second, you scan the remaining elements with an inner loop, j, and notice we start j at I plus 1 to make absolutely sure we never check the same pair twice. Third, you simply check if those two elements add up to your target.
The huge trade-off here, though, is time complexity. Checking every single pair gives us big O of n squared. Think about it. If your array has 10,000 elements, that is 100 million operations. I mean, sure, it works, and space complexity is just O of 1, but in a real interview, it's way, way too slow.
Section 2. The optimized solution, the one-pass hash map.
To really make this work, we need a specific mental model. It's called the complement. The complement is literally just the target value minus the current number we're evaluating. So for every number we look at, we just check if its required partner, its complement, already exists in our dictionary.
Let's do a quick dry run. Okay, we're looking for a target of 9. We check the very first number, 2, which is at index 0. Its complement is 9 minus 2, which is 7. Now is 7 in our hash map? Nope. The map's totally empty right now. So we just store the current number, 2, and its index, 0, right into our map, and we move on.
Now for the very next step, we move to the number 7 at index 1. Its complement is 9 minus 7, which gives us 2. So we check our hash map, and boom, aha! The number 2 is already sitting right there at index 0. We literally just found our match, returning indices 0 and 1 in a single, clean pass.
Section 3. Python implementation. Clean, interview-ready code.
All right, first we define our function. Notice we're using clear type hints here for readability. Then we initialize an empty dictionary called scene. Next, we loop through the array using Python's enumerate function. Honestly, this is incredibly useful because it hands us both the index I and the value num at the exact same time. Once inside the loop, we hit the core logic. We calculate the complement by just subtracting num from the target. Then we check, hey, is that complement already in our scene dictionary? If it is, we hit an early return, handing back the index of the complement alongside our current index I.
Now, if the complement isn't there, we just add the current num and its index I straight into the dictionary. But notice something absolutely crucial here. We insert this after we check for its complement. Doing it this way cleanly prevents us from accidentally using the exact same element twice. And then we just finish with a default empty return as good practice.
Section 4. Complexities and pitfalls. Preemptive debugging. Let's take a second to contrast our solutions. We took the brute force time from a really sluggish O of n squared all the way down to an average O of n, linear time. How? Well, we achieved this by trading off space. We increased our space complexity to O of n for the hash map. But just a quick note here. While average time is O of n, hash collisions can technically make the worst case O of n squared. It's super rare, but definitely good to know.
Look, under pressure, candidates make mistakes. It happens. But watch out for these specific traps. First, do not reuse the same index twice. Second, make sure you actually return the indices, not the values themselves. Third, be super careful not to calculate the complement backward. It has to be target minus num. And finally, don't overthink it. Hash maps naturally handle negative numbers and zeros just fine.
Oh, and here is a massive pro tip before you write a single line of code. Always clarify with your interviewer whether the array is sorted or if multiple solutions could exist.
Doing this is huge. It demonstrates structural senior-level thinking rather than just showing off that you memorize the answer.
Section 5. Summary and Next Steps. Master the pattern.
Your core takeaway today is the hash map paradigm. A single pass through the data, using a little extra space for constant time lookups, which dramatically reduces your execution time. Honestly, mastering this exact pattern is your foundation for much harder problems down the road, like 3-sum or subarray sum.
So, we optimized a sluggish brute force approach right into an elegant linear time hash map. Now, the challenge is completely on you. Try implementing this cleanly, entirely from memory. Think about it. If you can't build this solid foundation today, how are you going to handle the really complex variations tomorrow? Give it a shot. Thanks for watching this explainer. Happy coding.